evening, everyone. Am I audible? Hello, am I audible?
Yes, ma'am.
Okay, thank
Yes,
you.
ma'am.
So, let us start the session. Today, we will be covering the week 2 content of the linear algebra course. So, we will just go through the basic concept that you have already studied in the week 2, and then we will solve some sample problems. So, you can ask any doubt in between. Otherwise, like you can unmute and ask the doubt at any time. So let me start the session. So I hope my screen is visible for everyone, right? Okay.
Yes, ma'am.
Yeah. So this is the week 2 content. Before starting, let me introduce myself. I am Harsha. I am a research scholar from IIT Tirupati. Okay. Now, first we will go through the concept that we have covered in the week 2. So we will just go through the concept. We will not explain the proofs and everything for theorem. We will just go through, we will just take the theorem and the definitions, and we will, when we go through the questions, you can ask the doubts if you want, and at that time, if you want, we can cover the concept once again. So, in the last week we have started with some matrix operation or reduced form of a matrix and all, and some linear equation, system of linear equation and all. So this week actually starts with some operations on the identity matrix. So to reduce a particular matrix A, we can do the same kind of row reduction operation in the identity matrix, and then pre-multiply the identity matrix, the row reduced form of identity matrix, to the original matrix. So before that, let me write what are all the possible operations in a matrix. So we have three kinds of operations in the identity matrix. So the first one we will notate by Eij. Eij, what does Eij represents? The interchange of I and j. Interchange of rows I and j. So interchanging the rows I and j is denoted by Eij. And the second operation is given by E alpha I. Okay, E alpha I means multiplying the ith row with a scalar alpha. Multiplying the ith row with a non-zero scalar alpha. Non-zero scalar means just a constant multiplication. And the third one is E I plus alpha j. What does this means? We will multiply the jth row with the scalar alpha and then add with the ith row. Okay, replace the ith row with the addition of ith row plus alpha multiple of jth row. So these three are the operations in the identity matrix. Usually in any matrix we will do this kind of operation in order to get a row reduced form. So instead of doing that a particular matrix, what we can do is we can do the corresponding operations in the identity matrix and then pre-multiply it. For example, what we can do is if A is a matrix and I and J are two rows, the interchange of I and J denoted by Aij. Aij is same as Eij into A. A is our original matrix. Okay, so multiply A with the Eij, that is Ij rows of identity matrix are interchanged, and then what we are obtaining is Aij, where Aij is the matrix which is obtained by interchanging the ith row and jth row. Okay, so instead of doing the operation for A, we can do it for identity and then do like this, pre-multiply with A. So that was the one thing we covered. And also whatever the matrix we are obtaining from the identity matrix using these three operations here, and these kind of matrices are called elementary matrices. So the first theorem states that let A be an m by n matrix then there exist elementary matrices E1, E2, etc. En such that En, En minus 1, etc. E1A is a row reduced form. So the row reduced form of A can be obtained like this, that is by pre-multiplying with a set of elementary matrices, the row reduced form of A can be obtained. That is what this theorem says. Now the next concept we have reduced row echelon form. For short we will write RREF. Okay, so in the last class we already studied what is row echelon form. So here we are studying reduced row echelon form. So first of all, for the reduced row echelon form, it should be A should be in a row echelon form. So I hope you remember what is row echelon form. Okay, and in the row echelon form we have already seen a pivot. Pivot means the first non-zero entry in each row, and that should be equal to 1. So for row reduced echelon form, the pivot should be equal to 1. Pivot should be equals 1. And the third condition is any column containing a pivot should have no other non-zero entry. For example, if we have some matrix and suppose here it is 1 in the second row, the second element is a pivot. Okay, then we should make above and below of this. Everything should be 0. Okay. So in the row echelon form, what we were saying is Below the pivot, everything should be 0. But in row reduced echelon form, what we are saying is above the pivot and below the pivot. So all the columns should be 0 except the pivot. The column containing a pivot should not contain any other non-zero element. That means pivot is the only non-zero element in that column. Yeah, so after that we have found some method to find an inverse. So I am not going to explain that method. I will just write it. Find. Suppose if A is a matrix, what is inverse? The matrix A into A inverse equal to identity. So whatever the A inverse, that is the inverse of A. If A is a matrix and B is a matrix such that both are n by n matrix, suppose. Inverse is defined for square matrix only, such that AB equals BA equals identity matrix, then B is called a inverse. Inverse of A. Okay. So we have one method to find the inverse here. We will write A and with A we will write identity. So what we are writing is just write the matrix A and just adjoin the identity matrix to it. Okay. And then reduce it. So after some stage of reduction, if A is invertible, what we will get is the first, instead of A, after the reduction we will get I, identity. Okay, and here we will get A inverse. Okay, if A is invertible, then we will get some expression like this. So we should reduce the matrix AI such that the first, instead of A we should get I here, and whatever obtaining here is the inverse of A. Okay, and now we will see what is the rank of a matrix. Can anyone say what is the rank of a matrix?
Rank of the matrix is nothing, it is just the number of non-zero rows.
Yeah, number of non-zero rows in the reduced form. First we will,
Reduced to infinity.
yeah.
Yeah.
So number of non-zero rows in the row echelon form or reduced row echelon form. Anything is okay. So that is the rank of a matrix. And using the rank, actually we can say for a system how many solutions are there. That means if we are given a system, then we will find the rank of the corresponding augmented matrix of the system, and using that we can say the system has how many solutions. That means either unique or there is no solution or infinite solution. So let us see. Consider Ax equal to B. We already know if we have a system of equation, we can write it in a matrix form like this, Ax equal to B. Okay. Now we will consider the augmented matrix AB. Okay. And we will reduce it to the corresponding row echelon form. Then we will get some matrix A tilde B tilde. So A tilde B tilde is a row reduced form of AB. Okay. Now, uh, these two systems are actually equivalent. Okay, in order to find the solution of Ax equal to b, it is enough to find the solution of A tilde equal to b tilde. Okay, that is why we are reducing to row reduced form. So, using this A tilde B tilde, we can say, using the rank of this matrix, we can say how many solutions are there for this system. So, first one is, if rank of A tilde B tilde equals rank of A tilde equals n. What is n? A is an m by n matrix. Okay, m rows and n columns. This columns n means there are n unknowns. Okay, that means here n means either the number of columns or the number of unknowns x1, x2, etc. xn. Okay, if the rank of A tilde B tilde and rank of A tilde both are equal to n, then we have a unique solution. Okay, that is the one case. And the other case is, we can have rank of A tilde B tilde is strictly less than rank of A tilde. Sorry. Rank of A tilde strictly less than rank of A tilde B tilde. Okay, that means for a matrix A tilde B tilde, if we are considering A tilde only, it has a rank which is strictly less than rank of A tilde B tilde. So what we will get? For A tilde, we will get a 0 row. Corresponding to that, the B value is a non-zero. So the corresponding equation will be 0x1 plus 0x2 plus etc. 0xn equal to some non-zero value. That means that system is inconsistent. It does not have a solution. Okay. So in this case, no solution. System is inconsistent. Okay. And the third case is uh, rank of A tilde B tilde is equal to rank of A tilde. Rank is equal, but it is strictly less than n. Strictly less than number of unknowns. In that case, there are infinite solutions. Okay, so only these three are possible for a system of solution. There will not exist any case which has finite solution other than that uniqueness. Okay, so we covered all the three cases how the system can have solutions. Now, what is a homogeneous system? Homogeneous system?
Ax is equal to 0.
Yeah, Ax equal to 0. It is the homogeneous system. So, non-homogeneous means? What is?
Ax is equal to b.
Yeah, Ax equal to b with b not 0. Okay. In this case, what we should note, in the first case, homogeneous system, Ax equal to 0 always has a solution. It has a solution x equal to 0. Okay, solution is guaranteed here. It can have more solution other than the 0. It can have non-zero solution also. But in the homogeneous case, always existence is guaranteed. But here we can have uh, anything. That means it can have solution, no solution, or infinite solution. Okay. Now we will see vector space. Actually, vector space has a more elaborated definition, but here we are just, as of now, we are just dealing with a very small definition, a small case. So, what it actually says that we are just dealing with the cases Rn. That means r cross etc. n times. Okay. Vector space means there are various cases. It is not just Rn. Okay, we will just deal with the Rn only now. A subset V of Rn is called a vector space if,
One question.
yeah,
Rn itself a vector space?
of course, it is a vector space.
Okay, so V is a subset of that vector space and V is also a vector space.
No, we are saying a subset is a vector space if some conditions are satisfied. Okay, that condition is
Okay.
what I am stating here. AV plus BW belongs to V.
Okay,
Okay,
okay.
where
Yeah.
A and B are some real numbers and V and W are we are taking from V. Okay. Now, for example, if we are considering Rn itself, Rn itself, if we are taking, I am taking an element x1, x2, etc., xn and y1, etc., yn in R. Okay, so we are taking Rn. Rn itself a subset of Rn. Okay, and we are taking two elements. Say this is V and this is W. Okay, and two scalars, constants AB in R. Okay, if A into x1 etc. xn plus B into y1 etc. yn belongs to Rn. If this condition is satisfied, then Rn is a vector space. Okay, that is what our definition says. Now, what is this value? This is ax1 plus by1, ax2 plus by2, etc. axn plus byn. Okay, so it has n coordinates. So obviously it belongs to Rn, right? So Rn, a subset of Rn, it satisfies the condition AV plus BW belongs to Rn. So Rn is a vector space. Okay. Now we can give one more example. For example, I am giving V equal to set to 1 1 0 1. Okay. It is a set consisting of only two elements. Okay. Is this a vector space? This is a subset of R2. Correct?
Yes.
So, if it is a vector space, what is the condition? If we are taking some linear combination of elements, it should belongs to V, right? Now, let me take the element 1 1 plus 0 1. Okay. Here I am taking two elements from the V, set to V. V subset of R2. I am taking two elements V equal to small v equal to 1 1 and W equal to 0 1 and two scalars same. Instead of A, B scalars, I am taking 1 and 1 belongs to R. Sorry, belongs to R. That is here A equal to 1 and B equal to 1. So what we told, AV plus BW belongs to V. If this condition is satisfied, V is a vector space. Okay. Now let us see whether this condition is satisfied or not. Now here A equal to 1 and V equal to 1 1. So 1 into 1 1 plus 1 into 0 1. So what we will get is 1 1 plus 0 1 which is equal to 1 2. Is this belongs to our set to V? set V consists of only two elements, right? The set V is the element 1 1 and 0 1. Okay, so 1 2 does not belongs to V, correct? So V is not a vector space. Is this clear? Is this clear, the concept of vector space?
Yes, ma'am. But recall once, ma'am.
Sorry, can you repeat?
Yes, ma'am. Understood. But recall once. It will be good now.
Okay, okay. So what a vector space means, a subset of Rn. We are dealing with only subset. So we just need to consider this condition now. A subset V, a subset V of Rn, it is called a vector space if some conditions are satisfied. And that condition is stated below as AV plus BW belongs to V whenever if A, B belongs to R. A and B are real numbers and V and W are elements from the set V. Okay, set V we have taken here. And now, if we are taking Rn, Rn itself is a subset of Rn. Okay, if we are given any subset of Rn, to check whether that subset is a vector space or not, we need to check whether AV plus BW belongs to that subset. Okay, now we are taking the set Rn, V is Rn, and two elements, V as x1, x2, etc. xn and W as y1, etc. yn. Okay, these two elements. And scalars we are taking sum A, sum B. It can be 1, 2, 3, minus 1, anything. Okay, it is from real numbers. Then we are taking the linear combination. Linear combination means this kind of forms that we have already seen. What is a linear combination? Okay. So if it belongs to the set Rn, so here Rn is V. V subset of Rn we have taken as Rn itself. So if we are considering Ax plus By like this, what we will get? Ax1 plus By1, Ax2 plus By2, etc. Axn plus Byn. Obviously it also belongs to Rn, right? It has n coordinates. So it belongs to Rn. So Rn is a vector space. Now we are considering a subset of R2 like this. V equal to 1, 1 and 0, 1. This means only two elements are in the set V. We need to check whether V is a subspace or not. So this is actually not a subspace. If it is not a subspace, what we need to prove? We should have two elements and two scalars such that its linear combination does not belongs to V. If all the linear combination belongs to V, it will be a vector space. Okay. So we are considering two elements. Okay, there are only two elements in the V. So I am taking that two elements, V equal to 1, 1, W equal to 0, 1. If it is a vector space, it's addition. Addition means adding these two elements means it is a linear combination, correct? So I am just adding 1, 1 and 0, 1. So 1, 1 plus 0, 1, 1, 1 plus 0, 1, what we are getting? 1, 2. Okay. This 1, 2 does not belongs to V because V contains only two elements, 1, 1 and 0, 1. Okay, so 1, 2 does not belongs to the set to V. So clearly V is not a vector space. So that is the concept of vector space. If we have a set, if we are taking all the linear combination of the set, so whatever we are obtaining, so we will call the set of all linear combination as the span of S. Okay, that span of S will always be a vector space. Okay. So this is the concept vector space. Now, actually in R2, Okay, what are all the subspaces of R2? Okay, or subspaces of R2, or equivalently you can say vector spaces. So subspaces, it is not a new term actually. What it says is, it is itself is a vector space and a subset of R2. Okay, so what are all the possible vector spaces in R2? Can anyone say? R2 means our plane. Any idea what can be the possible vector spaces in R2?
Singleton 0, 0,
Yes.
straight lines passing through origin, and R2 itself.
Yeah, there are only three possibility straight lines through origin and R2. So actually there are only three possibility for a subspaces of R2. One is the null space 0, 0. It contains only the identity 0, 0. And the straight line passing through origin means the lines like this. Okay. This kind of lines, x-axis, y-axis, everything will be subspaces and or vector spaces, and R2 itself is a vector space. So for the proof, maybe we will learn later. Now we can leave the proof. And for okay, by the way, one question. Is any straight line a vector space? Okay, we already told only. Of course it is no, because we told if it passes through origin, then only it is a vector space. For example, I am asking the line L such that x equal to 1. So it is a line. So how the line is? X equal to 1. Okay, this blue is the line x equals 1. Okay, is this a vector space in R2?
No, identity is not here.
Yeah, of course identity should be there. Identity 0, 0 does not belongs to L. Okay, identity should be in a vector space. So or if we are just using the definition, what we can say is, actually in the definition we haven't mentioned that identity, it is actually understood, but still actually we can say that, for example, 1, 0 and 1, 1. Okay, so 1, 0 is this point and 1, 1 is this point. These two belongs to the line L. But if I am adding these two, 1, 0 plus 1, 1, okay, the linear combination, that AB plus BW, that is 2, 1. That it actually it is here 2, 1. It does not belongs to L. Correct? So it is L is not a vector space. So that is the reason actually only straight line through origin will be the vector spaces. Now we will say what is the linear combination and the linear span. Okay, I already told what is a linear combination. If V1, V2, etc., Vn Vk are elements of Rn. Okay, we have k elements in Rn, and C1, C2, etc., Ck are scalars. Scalars means the elements from the real numbers. Okay. Then C1 V1 plus C2 V2 plus etc. Ck Vk. Okay. This is said to be the linear combination of elements V1 etc. Vk. Okay, linear combination means just multiply each element with some scalar and add this. Okay, so all the possibility are called a linear combination. And if we are collecting all the possibility, that means all the linear combinations, then the corresponding set what we are obtaining is called the linear span. For example, if we are writing the set S equal to V1, V2, etc. Vk, each Vk in Rn. Okay, then we call span of S or linear span of S. Okay, let it write it as L of S, linear span of S equals set of all A1 V1 plus A2 V2 plus etc. plus AK Vk, where ai belongs to R for 1 less than or equal to I less than or equal to k. If all ai are scalar, that is real numbers, the set of all linear combinations like this a1 v1 plus etc. ak vk is called the linear span of the set S v1 v2 etc. vk. Okay. Now we will give a definition of basis also. Basis of a vector space. If V subset of Rn is a vector space and B subset of V such that linear span of V equal to V and there is no So what does this means? If we have a vector space V and a subset B of V we are taking, okay, and if the linear span of B, that means we are taking all the linear combination of the set B, okay, if that linear combination, the set of all linear combination is same as the sub vector space V, okay, and if no proper subspace of B does not span the space V, then it is called a basis. That means if B equal to V1, V2, V3, okay, and span B equal to V, okay. Now, if span of V1, V2 is also V, then B is not a basis. Okay, this is what the second condition says. Okay, if a subset of the B, V1, V2, if it itself spans the space V, then the B cannot be seen as a basis. Okay, now if this condition is not satisfied, that means V1, V2 does not span vector space, V1, V3 does not span the vector space, or V2, V3 does not span the vector space. That means whole V1, V2 and V3 are essential to get all the elements of V. In such a condition, we will call B is a basis for the vector space. Okay. So these are all the basic condition that we have, basic concept we have seen in the last week. So let us go to the questions. Okay, so the first question is, we will see the reduced row echelon form. So which of the following are reduced row echelon form? So first question, okay. So what about the first one? Yeah, is this in reduced row echelon form? Not row echelon form, reduced row echelon form.
No, first one is not a row reduced echelon form
Yeah.
because second column pivot element is 1, and in this column all elements must be 0.
Hmm.
But one that is in first row above pivot element is not equal to 0,
Huh.
so it is not a row reduced echelon form.
Yeah, so I hope everyone understood that. Here pivot in the first row this one is the pivot element, and in the second row this is the pivot element, and in the reduced row echelon form the column containing any pivot should have all other entries 0. But here in the second column the second element is a pivot, but the element above it, this one, okay, this is a non-zero element, so it is not in row reduced echelon form. Okay, now what about the second one?
Second one is, yes, it
Yes,
is row reduced echelon
yeah,
form.
it is very simple, it is row reduced echelon form. And now if I ask, okay, this is, yes, and what about third one?
Third is also, but fourth is not because in fourth pivot element is not 1.
Yeah, third is a row reduced echelon form. Here see in the second column we can see here a 1 is there, okay, but that does not matter in finding the row reduced echelon form. Only thing is corresponding to the pivot, that pivot should be 1, and corresponding to the pivot the corresponding column should have all other entries 0. Here corresponding to this pivot 1 and this pivot 1 we have all other elements 0. Here it is 0, here it is 0. Okay, so this 1 2 3 that does not play a role. Okay, and here what is the problem? 2, this 2 is the problem. The pivot is not 1. If we are changing this to 1 0 0 1, if we are dividing R2 by 2, what we will get, it is 0 0. In this case it is a row reduced echelon form. That is how we are finding from a matrix a row reduced echelon form. Okay, now let us see the next question. Second question is true or false. So question is, we have given a vector 1 minus 2 5. It is an element from R3. Okay, does this belongs to span of these three elements? Here the three elements are 1 1 1 1 2 3 2 minus 1 1. Okay, so how can we do this question? Any idea? Question is whether
We
this,
will
yeah,
try to write down 1 minus 2 5 in the linear combination of these three elements. If we will find the true real values according to like C1, first part plus C2 second plus C3 third part, then we can directly say that this vector space belongs to span of these three vectors.
Yeah, that is the idea. What we will write is, we will try to write it as a linear combination like this. 1 minus 2, 5 as a linear combination of given three vectors. Okay, if this given one is solvable for A, B and C. That means if we are getting some values A, B, C which satisfies this equation, okay, then what we can say, it is in the span of the set. Otherwise, it is not in the span of the set. So, how we will solve this? For this, we will use the linear equation. So, how we can write the linear equation here? Here it is a plus b plus 2c equal to 1 and a plus 2b minus c equal to minus 2, a plus 3b plus c equal to 5. Okay, how we are writing? We are equating coordinate wise. So this is the a into 1. First coordinate is a into 1 plus b into 1 plus c into 2. That should be equated to the first coordinate in the left side. Okay, it should be equal to 1. In the same way, we are equating second coordinate, third coordinate. So we obtain three equations in three unknowns. Now what we can do? We can write it in a matrix form. Okay, this linear system we will write in a matrix form. 1 1 2 1 2 minus 1 1 3 1 into ABC equals 1 minus 2 5. So if we are just multiplying the matrix, then we will go back to our linear system. Okay, that is the equivalent form. Now, how we will find the solution ABC exists or not? We will find the augmented matrix. We will consider the rank of the augmented matrix. Okay, and we have three conditions. It has a solution, no solution, or unique solution, like that. Let us see. So here what is the augmented matrix? 1 1 2 and 1 1 2 minus 1 minus 2 1 3 1 5. Okay, now we need to reduce it to the uh, row echelon form. So what we will get? Okay, do you want me to do all the calculation, or can you try it? If anyone want to do, we can just solve and see what are the, like, whether ABC value solution exists or not exist, or is it unique? Anything we can check. Or if the calculation is easy for you and you can find it, we can leave. So what do you want? Or if you want, you can just try in the next some 2-3 minutes. You can try. So do you want me to do this?
Yes, ma'am, you can go ahead, please.
Okay. Then I will just do it. So this is our augmented system. Now we will reduce it to its form. So first row, yeah. So second row. So first element we have kept it as 1. So what we need to do is, second row, first element should be 0. So second row we will change R2 minus R1. So 2 minus 1 minus 3 and minus 3. And the next one is R3 also should change to R3 minus R1, because this 1 should go to 0. So 1 minus 1 is 0, 3 minus 1 is 2, 1 minus 2 is minus 1, 5 minus 1 is 4. Okay. So the next step is 1 1 2 1, 0 1 minus 3 minus 3. Now we need to change this 2 to 0. Okay, so for that what we need to do, R3 changes to R3 minus 2 times R2. Here it is 0 minus 2 times 0 is 0 only. So 2 minus 2 is 0, and minus 1 minus 2 times minus 3, which is 5. Okay, and 4 minus 2 times minus 3, it is 10. Okay, so this is our row echelon form. It is not reduced row echelon form, it is row echelon form only. Okay, now what we are having, what is the rank of A and what is the rank of A bar, rank of A dash B dash. So this much is our A and this whole matrix is A bar B bar. Okay, what is the rank of A bar?
3.
Yeah, this is 3 because we have 3 non-zero rows here. And what is rank of A bar B bar?
3.
This is also 3. And what is n here? N means number of unknowns or number of columns.
Yeah, 3 only.
3 only. So these 3 are equal. Rank of A bar B bar equal to number of unknowns. Then what does that means? It has a
Unique
unique solution.
solution.
It has a unique solution. So, and we can find the solution easily from the last matrix. The last matrix says that 5C equal to 10. Correct? Okay, let me write it as 3 equations. So, what are all our equation? A plus B plus 2C equal to 1. Okay, that is corresponding to the first row 1 1 2 1. Okay, and corresponding to second row what we will get, B minus 3C equal to minus 3, and third row is 5C equal to 10, and from this we will get C equal to 2. Then we will back substitute the obtained value. C equal to 2 means B equal to 3C minus 3, so it is 3, and A equal to 1 minus B minus 2C, what we will obtain, 1 minus 3 minus 4, it is minus 6. So we obtain the value A, B, C as minus 6, 3, 2. Okay, so that was our problem. Find the A, B, C such that A into first vector plus B into second vector plus C into third vector. So let me show that. So yeah, the equation 1 was A into 1 1 1 plus B into 1 2 3 plus C into 2 minus 1 1. So we obtained the value A, B, C which satisfies the equation 1. So what does that means? The element in the right 1 minus 2 5 can be written as a linear combination because the value ABC real numbers exist, correct? It can be written as a linear combination of the 3 elements in the set. So this 1 minus 2 5 belongs to the span of the given set. So the statement is true.
Ma'am, one question. I haven't read the span so far. So, can you tell how span is different from vector space?
Uh, Yeah, actually, in this particular case of Rn, how this Rn is defined is as AV plus BW. It is also a case of span only. Uh, okay, I can say.
No, just at very just definition, like how are they different? Span and vector space. That's
See, vector space means if there is a subset of Rn, you need to check whether it is a vector space or not. To check whether it is a vector space, you will consider two elements from that set, and if AV plus BW belongs to V for AB in real numbers, then P is a vector space. That is a definition.
okay.
Okay. Now, what span means? Okay, this is the definition for vector space. Now, what span means? If we are
We
given
did
a
the
set,
same thing. We did the same thing for span also, no?
yeah,
In
span
the
also,
above.
in case if we are given a set S, okay, we
Mm.
are going to find the span of S. We are not going to check whether S is a vector space. That is the condition. What we are doing here, here we are considering V. We are checking whether V is a vector space or not. For that we will check this condition is true or not. Okay, if it is true, it is a vector space. Otherwise, not vector space. But in case
Yeah.
of span, we have some set. We are finding what is the span of S. Span of S is the set of all linear combination. ax1 plus
Okay.
ax2 plus etc. axk. These
Okay.
xk's are all elements of S, and a1, a2, ak. ai's are all elements of real numbers. This S and
Okay.
V
So
are different.
express any linear combination from the elements in S, then it belongs to the span of S.
Yeah, we will collect all the linear combination.
Okay.
Okay, the collection of all linear combination is the span of S. Obviously, span of S will be a vector space. Okay,
Okay.
because
Okay.
this condition is satisfied here. Linear combination belongs to this. But S is not a vector space. S need not
Okay.
be a vector space. Okay. For example, if I am taking S equal to just one element, one. Okay. Is this a vector space?
Uh, no, I mean we are taking it as a set of R2 element,
Huh.
and we are saying we want to find the span of this.
No, my question is this S is a vector space or not? Not span.
Okay. I uh, I
No, ma'am, because we don't have two elements, no.
Two element is not there, that does not matter. Like you can take both V and W as 1, right? V equal to 1, W equal to 1. That does not matter. For example, V equal to just the zero
does
element
not
we
have
are
an
taking.
identity element.
It is a vector spaces. Even though it has only one element, it is a vector space, right? Two element means it is just a representation. Only condition we need to check is all its linear combination also belongs to that set or not.
So
Okay.
any other linear combination if we make,
Huh.
it will not belong to this because one is just one, and any other thing we don't have in the set,
Yeah, if
right?
for
So it
example,
will,
if I am taking 2 into 1 plus 1 into 1, what I will get 3. It does not belongs
okay.
to S.
Yeah.
Okay, so this is not a vector space. Okay,
Okay.
this is completely different from vector space. Means for a given set we are checking condition to know it is a vector space or not. Okay, but what span is means if given a set we are defining something. Okay,
Okay.
span means set of four linear combination. Here only one element
Kind
is
of
there. A1
we
1
are
such
creating
that A in R.
we are we are creating a vector space kind
Yeah,
of, right?
from this obviously it is a linear combination, so we are getting it as a vector space. And what is this
Okay.
vector space? It is a line passing through the 1 right?
Hmm.
Okay, it
For
is,
an R for
yeah,
an R2.
yeah,
Hmm.
it is in R2. 1 means it is in R2. We are taking all the
Hmm.
linear combination means 1 is there, 2 is there, 3. In between also 3 by 2 is there. And if we are A is 0, we have 0 also. Okay.
So 0, 0 is a part of all the vector
Yeah,
spaces.
0 should be there. If you are having a set, actually first thing you should check is whether 0 0. That means whatever the 0 element. In case of R2 it is 0 0. In case of R it is 0. So whatever the 0 element, it should be in the set. That is the first condition actually. In case of Rn, as I told, like we have sufficiently reduced all the conditions of vector space, because in Rn it is a very easy case. But if we are checking the vector space, there are some 8 9 conditions to check a set is a vector space or not. So in that, the basic thing is whether the 0 element belongs to the vector space or not. That is the first condition actually. Okay,
Okay.
is that clear?
Yeah.
Okay. Now, okay. Now one more question. again true or false. If I have an element 1 0 1, does it belongs to span of 1 0 0 0 1 0? It is very easy, just by the observation you can say. 1 0 1 belongs to span of 1 0 0 0 1 0. Is this statement true or false? That is the question.
It's not right.
Yeah, it is not true. It is false. Because what if we are writing 1 0 1 as some linear combination a into 1 0 0 plus b into 0 1 0, what we will get? 1 0 1 equal to a b 0. What does this means? 1 equal to 0. This is wrong, right? See, the third coordinate is 1. If we are equating the LHS and RHS, third coordinate 1 equal to 0. Correct? That is wrong. That means there does not exist. Like whatever the choice A and B we are taking, we cannot write 1 0 1 as a linear combination of the given two elements. So,
Okay.
this statement is false. Okay, so actually you don't need to write all these steps. Just by examining you can say, because the third element is 0 in the set. In the set we have two elements. In both, third element is 0. So if we are multiplying with any scalar, that third coordinate always will be 0. But the given element 1 0 1 has a non-zero element in the third position. So obviously it will not be. So you can just see the question and say the answer. That's it.
Okay.
Now,
Yeah.
now I will do one question on. Okay, we will see some sets which are either vector space or not. So you have to tell whether it is a vector space or not. It will be which of the following are subspaces, or we can say vector spaces itself. That means we are considering Rn. Okay, in Rn I will give some subsets. So you need to say it is a vector space or not. So the first one is set of all x1, x2, etc. xn such that x1 greater than or equal to 0. So first one is set of all x1, etc. This is an element of Rn, such that the first element x1 is always greater than or equal to 0. Is this a vector space or not?
No, ma'am.
No. Reason?
Because by multiplying any negative scalar, that positive number will convert into negative.
Yeah. Like what she is saying is, if I am
like if I take element -1 into 1 into 2 into up to n, then first element will convert into negative part, that is in -1, and that will not fulfill our required condition of given set that we want to check it is vector space or not.
Okay, so let me explain this. For example, suppose we are taking 1, 2, 3, etc. n. It is an element in Rn. Okay, and also the first coordinate x1. x1 is here 1. It is greater than or equal to 0. So it belongs to, suppose this is V. So this belongs to our V. Okay, now what she is saying is, if we are multiplying with 1, 2, 3, etc. n, what we will get? -1, -2, etc. -n. Will it belongs to V? No, right? It does not belongs to V, because -1 is strictly less than 0. It does not satisfy this condition, the first element greater than or equal to 0. Okay, so whatever we told now is, take two elements, check whether the linear combination are there in the set or not. So instead of that, if you have confusion why we are taking just one element and just one multiplication like this, so this is also enough actually. For example, what is the condition here? We are taking the first element as 1 to etc n. Second element is 0 0 0 0. Okay. So obviously this condition also the same as the other condition, right? Is that okay? Why I
Um, can you explain it more, like maybe write down how we are reaching this conclusion?
okay. Uh, See here, what we are doing is, suppose V I am taking as 1 2 etc n, and W I am taking as 0 0 etc 0. Okay. Now, what our condition is, if AV plus BW, okay, belongs to the space V or the set V, then V is a vector space. Okay. Now we are taking A equal to -1 and B equal to whatever, suppose 1. Okay. So what we will get? AV plus BW equals -1 into, we are just substituting whatever we have taken. A is -1, V is 1, 2, etc. n. Okay. Plus B is 1 and W is 0, 0, etc. 0. And what is this? This is same as -1 into 1 to etc n. We already proved this element does not belongs to V because the first coordinate here is -1, right? X1 is
Yeah.
-1. It is strictly less than 0.
That does this mean that we have found a value of A and B scalar values which do not satisfy? So since we have found one value, this means that it is like that.
Yeah, we found one value like
Mm.
two vector VW and two values A and B such that the linear combination does not belongs to V.
We
Okay,
so we conclude. So,
we
but say
conclude.
suppose
Hmm.
don't assume the values of A and B,
Hmm.
then what is the method of finding A and B? Is it the same what we did, like finding a unique or infinite? That is the method of finding again if we don't assume the scalar values. So,
Can you repeat the question?
no, I'm just saying, say I want to find whether this is a vector space,
Hmm.
and I don't want to assume any values to begin with, like -1 and
Hmm.
and 1.
Okay.
Then how can I find the values without assuming initial values?
So in general, it is just because of intuition what we are saying. Like here in the
Hmm.
condition, we know x1 greater than or equal to 0. So we are checking whether if we are doing some calculation, will it belong always this x1 greater than or equal to
Yeah,
0. Okay.
it
For
won't.
example,
Um,
if I am taking an element, that is just like using the seeing the condition, we will get some intuition, right?
yes.
If I am
Yeah,
taking 1
correct.
1 1 and minus 2
Yeah,
2 2, obviously the
and
first element is going to be -1.
mm-hmm.
So it is not going
Mm,
to belongs to that one. Like that is like
correct.
we should take as per our discretion whether it can, like sometimes we will feel okay if I am taking just like 1 1 and all the scalar multiple of 1 1. Okay, definitely we know that what it is actually, it is a line through 1 1. If we are taking all the multiple, still it is going to be in that line only. Okay, if you are doing more problems like this, you will understand how it is, why it is coming, how it is coming and all.
Mhm.
Here it is like
Okay.
you can just think whether like it should not be very, sometimes it should not be very easy to find the uh,
For a beginner,
yeah,
supposing I'm a beginner, so I don't go by visual as like this. I don't go by that.
yeah,
Then
yeah.
is there a set method to arrive at that?
So only thing you can do is just the trial and error. Just take one, two elements and just do
I
the
see.
scalar multiplication or like addition
So
and check it is
okay.
again belongs to that set. or you can try different kind of combination. At some point you will understand, okay, if I am just changing this to this or this to this, it will not belongs to that. Something you will get, right? If you are doing some 2 3 linear combination.
Yeah.
So that is the only
Okay.
way we can say it is not a subspace. If it is a subspace, we can just prove, like we can just take the linear combination, it is there in the set, we can directly say. If it is not a subspace, only thing is we need to find the counter example. That means we need to find some scalar, some proper vectors such that it does not belongs to that one, that space.
Okay, thank you.
Okay. Now, okay, I will give next question. So you can just try for some 2 3 minutes, you can try, and then x1 x2 etc xn in Rn such that x2 equal to x1 square. Okay, so for 1 or 2 minutes you people just think whether it can be a vector. So suppose this is V, whether V can be a vector space or not. As I told, just try with 1 or 2 example, just add that, take any 2 elements, just add that element and check that the new element belongs to this vector space or not. Any element you try, it is just a trial and error method, and you try and say whether it is a vector space or not.
No, ma'am.
No. Okay, what about Swati?
I am still
Okay.
looking at it because I was just doing that one, then one, 2 4, like that I was doing. But
Yeah.
maybe I should switch the sign also and see.
Okay, you just
So
try with that 2 elements and check whether that addition belongs to this V or not.
okay, just a second.
Yeah.
Okay, ma'am, I think I got it. Yeah,
Yeah.
you've taken um, two sets, and then you've added them, two elements, and then added them, and so x square is not x2 is not equal to x1 square, so it is
So
not a vector.
not a vector space. So this is the way we have to do. Just try with some element, and if it does
Okay.
not work, like just change the elements. Like after doing something, we will understand, okay, whether it is going to work for every element, or if we are doing some modification, whether it is not going to work. That thing we will understand here, like for any element it is, we will get like this. So here we are taking 2 elements, suppose 1 1 1 etc in B, and the second element as 2 4 0 0 etc in V. Why it is in V? The second element always we can see x2 1 is a square of the x1 1. Here also the second element 4 is a square of 2. Okay, so we
Yeah.
are just adding. This is the linear combination 1 1 1 1 plus 2 4 0. What we are getting is 3 5 1 1 etc. So if it belongs to V, what is the condition? X2 should be equal to x1 square. Here 5 not equal to 3 square. X1 is 3 and 5 is x2. So 3 square not equal to 5. So it does not belongs to V, and the conclusion is V is not a vector space. Okay,
Yeah.
so one thing very easily to examine. So even before checking this 2 elements trial and error, in this condition, in this set, we have one idea, x2 equal to x1 square. This is a kind of some quadratic terms coming. In vector space, linear, everything means actually it should be some kind of linearity should be there. Okay, here some quadratic square term is coming means it mostly it won't be, not mostly actually it won't be a vector space. So that is also an idea. You can identify whether it is a vector space or not. To prove this,
Okay.
you should give some counter example like this.
Mm-hmm.
Okay, so if anyone else is having doubt, please ask on this. And now one more question. Set of all x1, x2, etc. xn such that x1 plus 3x2 equal to x3. So it is given x1 plus 3x2 equal to x3. We don't know about other elements, like it can be anything. There is no mention about that. So question is whether V is a vector space or not. Can anyone say by just looking at this?
Yes, since it is linear, so it will
Yeah,
be
it is
right.
linear, so
Okay.
our intuition should be it should be. Okay, so we can just see whether it will be. We will just write V, like they have given condition x1 plus 3x2 equal to x3. Okay, so we will take two elements. We will take two
Can we
elements.
take elements? Yeah.
So,
Yeah. Can we take elements, please?
elements means if we are proving it is a vector space, our intuition is vector space. So we should prove it for all elements. We cannot take some 1 1 1 1 2 2 2 2 and its linear combination is there. It is not the way. We should consider all elements. So we will just
I
assume
thought
x, y.
if one contradiction that will be enough, right?
Yeah, if we want to prove it is not a vector space, one contradiction is enough.
Then, okay, but if we want to prove it is, then we have to make it generic.
Yeah, so that is why I am taking elements as x1, x2, etc., xn, y1, y2, etc., yn. Two elements I am taking, some general
Okay.
elements, and two
Mm-hmm.
scalars I am taking. Okay, now we will do the linear combination a x1, x2, etc., xn plus b y1, etc., yn. So what is this? This is just coordinate wise addition ax plus by1 ax2 plus by2. Let me write the third elements also because it includes three elements in the equation. ax3 plus by3 etc. up to axn plus byn. This is the linear combination of two elements we got. So if it belongs to V, what should be the condition? See, the x1 etc. xn belongs to V. So this implies x1 plus 3x2 equal to x3. It belongs to V means the condition is satisfied. And y1 etc. yn belongs to V means what is the condition we have? Is that clear?
Yeah, I mean we want to check if this condition is satisfied even for the scalar combination. So so we have to take y1 also like that, right?
Yeah, y1 also we are taking because y1, y2 etc. also in V. So what
Yeah.
is the condition we are having? y1 plus 3y2 also
Y2 is equal to
y3.
y3.
Now
Yeah.
what we need to check whether this element belongs to V or not. Okay, so for that
Yeah.
we should consider the first element ax1 plus by1. So let me write ax1 plus by1 plus 3 times ax2 plus by2. What the condition says? First element plus 3 times second element should be equal to third element. Okay, if it satisfies, then this element belongs to V, right?
Yeah.
Okay, so now we will consider whether it is true or not. Now what is the LHS? LHS is if we are taking a outside, see x1 plus 3x2. Okay, x1 here I am taking, sorry, a from here I am taking, here I am taking. So what we will get, x1 plus 3x2. Just the rearrangement. Okay,
Yes.
because this is the condition we already know. We need to make this one to something related to this. So what we will do, we will take b outside, y1 plus 3y2, and x1 plus 3x2 we already know from this condition it is x3, it is ax3, plus y1 plus 3y2, from this we know by3. So we got the RHS, right? This side we got. Okay, so this element, the linear combination, belongs to V. This is true. So V is a vector space.
Vector space.
So we are taking for any element x, y, any scalar AB. It is not some specific value. So for any element it is true. So V is a vector space. Fine. If you have any doubt, please ask on this. Okay, otherwise I will give one more question. Xn such that x1, x2 equal to 0. Okay. What about this? Is this a vector space or not?
No.
No. Can you give some counter example now?
Yes,
Yeah.
in first part, if I take 1, comma 0, comma 0, all other elements are 0. And in second type, I take 0, comma 1, and all other elements are 0. Then
Yeah.
these two elements belongs to the given set because x1, x2, product of x1, x2 equal to 0. But sum of these two elements, we will get 1, comma 1, and all other elements are 0. But second element is also in that case. So x1, product of x1, x2 is not equal to 0. That is actually equal to 1. So this doesn't belong to given set.
Okay. So this is the thing we need to find x1, x2, y1, y2 such that x1, x2 equal to 0. Here x1, x2 equal to 0, y1, y2 equal to 0. But in their sum, whatever we are getting, here it is 1, 1 we are getting. Okay, it is 1 into 1 not equal to 0. So only thing is we need to consider the elements wisely. That's all. If we are just considering, okay, many element will work. If I am taking 0, 0, etc. No, actually if I am considering 0, 0, etc. and 1, 0, etc. both will belongs to V. But if I am taking the sum, again 1, 0, etc. 0, it also belongs to V. So if I am first trial is like this, I cannot conclude anything. Okay, then from this I am understanding, okay, maybe I can modify this to 1, still it belongs to V, but its sum is 1, 1, 1, etc. 1, 1, 0, 0, etc. It does not belongs to V. Okay, so that is how from one trial we will go to the other one and find the, check the conditions. Is that okay?
Yeah.
Okay. Now, okay, let us see. Okay, we have seen what a basis also. Let us see some example. Let us see some sets whether they are basics or not. Which of the following are? Which of the following? Forms.
Can you please explain basis once before starting?
Okay.
Thank you.
So, basis means V is a vector space. Like when we will say basis for a vector space. Okay. First of all, it should be some subset of V. This B is called a basis if first condition is span of B should be equal to V. Okay, that is the first condition. And second condition is if some B1 is a proper subspace of B. If I am taking not subspace, subset. If I am taking some subset of B, then span of B should not be V. That means it should be something inside V. It should not span full V. Should not be V. Okay, that means B is the every element in B is essential to form the V. Okay, if we are removing one element from V also, then the remaining element cannot span the whole V. That is the concept of basis. Okay. Now, actually, in the maybe the next week 3, you will learn one more definition for both are same actually. After learning the linear independence and all, you will learn the basis as the linearly independent set and it spans V. Okay, okay, that we will come to the next week. Okay, as of now, this is the definition of basis. Okay, now let us see some example. The question is, which of the following are basis 1 0 0 1? Is this a basis for R2?
Yes, ma'am.
Yes. So actually this is the very standard basis of R2. Okay. Why? We will see for first example why it is. If I am taking any element in R2, any element means I should represent it by some xy in this form. Okay. What I want? The span of, suppose this is our B. Okay. Span B equal to R2. This is our first condition. Condition 1 is span B equal to R2. Okay. Span B means set of all linear combination. That means A into 1 0 plus B into 0 1 such that AB in R. This is our span of B. What is this? Set of all AB such that AB in R. Okay. This is actually R2, right? Okay. This is our R2. That means if we are given any matrix xy in R2, we can write xy as a linear combination x into 1 0 plus y into 0 1. Okay. So that means any element belongs to span of the set B. So now next condition is any subset of any proper subset of B should not span R2. For example, suppose I am taking B1 equal to 1 0. Any doubt? Aman Chowdhury, any doubt? Okay. If B1 equal to 1 0. Okay. Now, is span of B1 is R2? Question. B1 is
No,
just
ma'am.
no, it is not a what the span of B1? Span of B1.
Span of B1 is just x-axis.
A span of B1 will be some form A into sorry. Okay. Okay, what was the question? B1 equal to B equal to 1 0 0 1 Okay, we proved that span of B equal to R2. That is what we have done. Now I am taking a proper subset B1 of B. It contains only one element, subset of B. Okay, now what is span of P1? Span of P1 is set of all A into 1 0, only one element. So all linear combination means set of all multiple of, so it forms set of all A0. That means any element in a span of P1 has second element as 0. So obviously it is not equal to R2. Okay. In the same way, if I am taking the other 0 1, if B2 is the set just 0 1, in that case also what we will get, span of B2 equal to set of all 0 A such that A in R. It is also not equal to R2. Okay, that means if we are taking any proper subset of this, it does not span whole R2. Okay, so this B is a basis. Okay, is that clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay.
Yes, ma'am.
Now
Okay.
next question. 1 1 2 2. This is B. Is B a basis of R2?
No, ma'am.
No, it is not a basis. For example, if I am taking some linear combination A11 plus B22, what I will get? A plus 2B, A plus 2B. Correct? It is in some form x, x. That means the first element and second element are same. Okay, both are same. But there are in R2, we have some element 1 0 in R2. Obviously, we cannot write 1 0 as a linear combination of these two, because any linear combination will give elements like this only. Correct? So, it is B is not a basis. Is that clear? Any doubt in this?
No, ma'am. No, ma'am.
Can you please explain the last part? So, which condition is it not satisfying?
The question is whether B is a basis of R2. If B is
Yeah,
a basis of R2, span of B should be equal to R2, right?
yeah,
Here, if I am taking span of B, that means linear combination of elements of B, I will
yes.
get it to
It is,
form A plus 2B, A plus 2B. That means first coordinate and second coordinate are always equal for an element in
yes,
span of B. But in
yeah.
R2, there are other elements which is not in this form. Okay, 1 0,
Oh,
first and second coordinate are different. That means 1 0 cannot be written as a linear combination of these two.
okay. So you
Okay.
mean to say if something has to be a basis for R2, it has to cover all the elements in R2?
Yeah, if that span, full span should be equal to R2. Here we are getting it is just a subset of R2.
Yes.
Correct? Actually, it is a
Okay.
subspace. Spans mean it is a subspace. Okay. But it does not form sole elements in R2 by linear combination. Correct? So it is not a basis. First condition is that the linear combination should give all elements of R2.
All elements it should give, right?
Yeah, it should give.
Okay, which is not giving because it is giving a proper subset.
Yeah, it is giving a proper subset. Some elements are in R2 which is
Okay.
not the linear combination of these two. Correct?
So the first condition is getting violated here.
Yeah, first condition is not true. Span B equal to R2. This is not satisfied here.
Okay, fine. Thank
Okay.
you.
Now, let me check. B equal to the same one, I have 1 1 2 2 and I am adding 1 0 also. Now is this a basis?
No, ma'am.
Still it is not a basis. One thing is, actually we can check span of B equal to R2 will be satisfied. Okay, just check this, span of B equal to R2. How you will check this? Okay, I will just give the idea, you should check it. Take XYZ, it is an element in R2. Okay, sorry, XY is an element in R2 and write it as xy equal to a into 1 1 plus b into 2 2 plus c into 1 0. If possible, if ABC elements exist such that for any element it is in this form, then we can say span B equal to R2. Actually this is true. Okay, this is what I want you to check. Just say that span B equal to R2. Do this. Now, but still it is not a basis. Span B equal to R2, but it is not a basis. What is the reason it is not a basis?
First two elements are linearly dependent here in
Yeah,
this
it
part.
is. Okay, if you are not coming to linearly dependent, because we haven't gone through this linear dependent independent, so everyone might not be knowing that. So can you say the condition that we already used? What we used, the span of B equal to R2 and one more condition, right? So using that, can you
Now,
say?
if we take proper subset of B, like in first element 1, 1 and 2, 2, same as in previous case, so this will not span our R2. So according to your second condition, this will not make a basis.
No, I am not saying any subset should span. Yes, some noise is coming. Can you mute? Yeah. See, what she is saying is span of, okay, first condition span B equal to R2, that is satisfied. Now next condition what we are checking is 1 1 2 2. It is not equal to R2. Will it imply that B is not a basis?
So the second condition.
So
So
second condition what it says is, if there exists a basis, there exists a subset. Okay, for example, there exists a subset B1 subset of B, that is proper subset such that span of B1 equal to R2. Okay, that implies the bigger set B is not a basis. That is the second condition. So
we can take for second condition 1, 1 and 1, 0.
Yeah, that is the set B1. We should B1 should be 1, 1, 1, 0. It is a proper subset of 1, 1, 2, 2, 1, 0. Okay, this is our B. And we can prove that this B1 actually span whole of our R2. Okay. Now, how can we write this span, this B1 spans R2? We will take an element XY in R2. Okay. And let me write it as, I am supposing, okay, there exists a linear combination A11 plus B10. So what I will get? A plus B, A. Okay. So that implies y equal to A and x equal to A plus B. From this what we will get, since A equal to y, I can write it as y plus B. From this B equal to x minus y. Okay, let me explain once again. We are starting with an element xy in R2. am assuming there exists a linear combination xy equal to a into 1 1 plus b into 1 0. Okay, now I should say I am just assuming some a b are there. I should say what is this a and b, does it exist or not. For that I should find what is the value of a and b in terms of our given x and y. So a into 1 1 plus b into 1 0 means a plus b a. From here we are equating y equal to, here x equal to a plus b, x equal to a plus b and y equal to a. So a equal to y, this is our one condition, and from this we will get b equal to x minus y. Now let me write a into 1 1 plus b into 1 0 equals a is y. Okay, y into 1 1 plus x minus y into 1 0. Okay, what is this? Y plus x minus y plus 0, which is x comma y. That means if I have given any element xy in R2, I am able to find a and b. A and b are given as a equal to y. This a and b I am giving in terms of given x and y. A equal to y and b equal to x minus y. For any xy, if I am taking the scalar a equal to y and b equal to x minus y, I can write xy as a into 1 1 plus b into 1 0. Okay, so the proper subset b1 of b itself span the whole R2. Okay, a proper subset of b spans R2. So b not a basis. Is that clear?
Yeah.
Here the first condition, span of b equal to R2, is satisfied, but the second condition, a proper subspace does not span R2. Okay, that is not satisfied because proper subset span the whole R2. So the second condition is violated, and so it is not a, the b is not a basis. Actually b1 will be a basis. You can check that b1 is a basis. Okay.
Okay, ma'am.
Yeah. Okay, if you want you can just try this also. Okay, 1 2 2 1. Okay, maybe you can just answer this whether it is a basis or not.
Yes, ma'am.
Yeah, it will be a basis. Yes, it is a basis. So just verify this. What you want to check is first prove that span b equal to R2, and then consider a single element, whether the single element spans whole R2 or not. So these two conditions you just verify. The thing is you should do all the problems like this, then only you will get used to it and you will understand what exactly basis means, like in what sense we should take elements, that all. Okay. Now next question is let y1 equal to set of all xy such that x equal to y, and y2 equal to set of all x minus y such that x equal to minus 5. Find a basis for y1 and y2. The second question is let S equal to y1 union y2, find span of S. Okay, so we have given two sets. Okay, before going to this, let me explain what it actually geometrically says, then maybe it will be easy to understand. What is the first set y1? Y1 equal to set of all xy such that x equal to y. Geometrically, what you can say about that set? What is that?
It's a straight line passing through the origin.
Ah. So the equation of straight line is?
Uh, x is equal to y.
Yeah, that is what is given in the condition, x equal to y. So this is our x equal to y. Okay, so that is our space y1. Y1 means the straight line, the line. Now, can you just say what can be the basis of y1?
1,
1 comma
1.
1. Okay, because any element, see, y1 is the set of all xy such that x equal to y. Okay, if we are taking this condition to here, what we will get? Set of all x, y is same as x, set of all x. Okay, that means only one element 1 1. It is enough to span of 1 1 equal to y, correct? Because if I am multiplying x into 1 1, what I will get? X. Okay, so if I am taking all such collection, this is the span of 1 1 means set of all linear combinations of 1 1. That means only one element means all the scalar multiples. So this is our y1, and other a smaller set than 1 1 cannot span. For example, 1 1 2 2. If I am taking this, span of 1 1 2 2 is also our y1. But a smaller set 1 1 can generate whole y1 or span whole y1. Okay, but a subset of 1 1, a subset b of 1 1, if b is a proper subset, then span of b not equal to y1. A proper subset of 1 1 means it is an empty set, right? It is not going to generate any set, any element. It is just like empty. So what we can say is 1 1. This 1 1 is a basis. Is that clear? Why 1 1 is a basis?
Ma'am, can you explain the last part? The second condition is not very clear to me. Can you just help me understand that?
So first condition is okay, right? 1 1 span whole y1.
Yes.
Yeah. Now
Yes.
second condition says there should not exist a proper subspace which generates whole y. So if possible, what is the proper subspace of the set 1 1? What is
For
it?
subset, zero, empty.
Empty set.
Okay.
In empty set, what we can say about linear combination? Nothing is there, right? There is no element
Okay.
in the set. It is not
Uh,
going to generate something, obviously.
so it is
Okay.
not going to represent the space. So that's why it is satisfying. It is a basis.
Actually, we can say by convention it is going to generate 0 0. Means maybe we can say, but it is not the proper way. Okay.
Okay.
As
Okay.
of now, anyhow, it is not going to generate whole y1, right?
Yes. Yeah.
Okay, because
Okay.
there is no element which generates y1. Empty set does not have element which can generate whole y1. Correct? So
Yeah.
the 1 1 is needed. It's essential to generate y1, like at least one element. So this
The
is a
second.
basis,
Okay.
and it is not a unique basis. 2 2 is also a basis, right? 2 2. This is also a basis for y1.
Okay.
Okay. So
Yeah.
basis is not unique. We can find different bases, but elements in number of elements in basis actually always will be unique. Number of elements
Okay.
in a basis. Now, what
Yeah.
was our second set y2 equal to set of all x minus y. Sorry, xy such that x equal to minus y. So this is xy. Okay, set of all xy such that x equal to minus y. So
Yeah, this also same. If we take, then it will be 1 minus 1.
yeah,
Or,
just 1 minus 1 is enough.
hmm.
Okay, just by looking at the set, now we are able to say what is enough to generate y2. A subset of B, a proper subset of B cannot generate y2, and B obviously generate span of B equal to y2. Okay, now next question was if S equal to y1 union y2, find span of S. Now can anyone say about this? What is the span of S?
Span of S basically linear addition of linear combination of y1 and y2 elements.
Yes,
So in y1 elements, y1 set elements are like x comma x,
x comma
and
x.
and in y2 set elements are like x comma minus x.
Yes, x comma minus x.
Yes. So if we take linear combinations of
Hmm.
these two,
Hmm.
then we can construct span S.
We cannot.
If we take linear combination of these two type elements and
Ah.
combination of all these, and we can collect all these combinations,
Hmm.
then we can construct span S.
Yeah, we can construct. My question is, what is span S? Like, obviously, we are collecting all the linear combination, right? Linear, like this is a subset of R2, and this is a subset of R2. Okay, that means one
So
is a line X. Okay, and next one is the line something like this. Correct? These are the two lines y1 and y2. Obviously, y1 is a subset of R2, y2 is also a subset of R2. I am asking if span of y1, like span is always a subset of R2. Span of y1 union y2 is a subset of R2. Any doubt in this? Hmm?
no, ma'am.
This is clear, right? And it is a vector space. Any doubt in that? We have two things, y1 union y2 if we are taking. Span of any set, not any set, like y1 and y2 are subsets of R2. So y1 union y2 is a subset of R2. We are taking all the linear combination of some elements of R2. So it is also a subset of R2, right? This is the condition. That is the one condition. Next question is, next thing is span of y1 union y2 is a vector space. If we are taking any set and its span, that span will always be a vector space. Okay, this is our second condition. Okay, so we are getting span of y1 union y2 is a vector space in R2. Okay, now my question is, what is this vector space? It is a vector space. What is this vector space? Is this a line, or is this R2, or is this a null space?
I think the entire R2 it will cover, but
Yeah,
I'm not sure.
it will cover entire R2.
Yeah,
Okay,
because yeah,
for example,
graphically, I'm just saying graphically, but I don't know the mathematical how it will derive. But just looking at the graph, if we do a combination, the vectors will go all around the axis, right? So
yeah, if we
y1,
are taking all the linear combination, it should cover actually all, like geometrically it is clear for you. So let us
whole
see how
plane.
analytically we can prove that.
Okay,
Okay,
yeah.
yeah. So for example, I am taking an element 1 1 in y1. Okay, an element 1 minus 1 in y2. Okay, now a into 1 1 plus b into 1 minus 1, it should belongs to span of y1 union y2. Correct? y1 union y2, it contains the element 1 1 and 1 minus 1. So if I am taking a linear combination like this linear combination should belongs to the span. Okay. Now,
Yeah.
let me take any element in xy in R2. Okay. Now, I am going to prove that xy I can write it as some a into 1 1 plus some b into 1 minus 1. So, for what a and b, I can write xy as a linear combination of 1 1 and 1 minus 1. That is what we are going to check now. So, what is this? This is a plus b and a minus b. Okay. So, the given element is xy. I need to find what scalar a and b will work for this equation. Okay. So, I need to find a and b in terms of the given x and y. What is this? A plus b equal to x and a minus b equal to y. So if I am adding these two equations, what I will get? 2a equal to x plus y and a equal to x plus y by 2. Okay, and b should be equal to x minus a from this equation. That means x minus x plus y by 2. Okay, so what I will get? 2x minus x minus y by 2, which is equal to x minus y by 2. Okay, so I got a equal to x plus y by 2 and b equal to x minus y by 2. So if I am taking any element xy, I can write it as x plus y by 2 into a into 1 1 plus b into 1 minus 1. A into 1 1 plus b is x minus y by 2 into 1 minus 1. So what is this? X plus y by 2 plus x minus y by 2. That is x. Here x plus y by 2 minus x minus y by 2. It is y. Okay. So any element xy in R2, I can write in this form. But this actually belongs to span of y1 union y2. Correct? Because 1 1 and 1 minus 1 belongs to y1 union y2. So, this linear combination should belongs to span of y1 union y2. Okay. So, any element in R2 is belonging to span of y1 union y2. What does this means? R2 is actually contained in span of y1 union y2. But we already proved that or we already know that any span is actually a subspace of R2. Okay. So from these two conditions, what we can conclude? Span of y1 union y2 equals R2. Okay. Is that fine for everyone? Is that okay for any?
Not fully clear, ma'am, but I don't know if we have time.
Yeah, we can explain for some 2-3 minutes also if you want.
Okay. Thank you.
Okay. Okay, where do you have the doubt exactly? Can you let me know?
Actually, yeah, sure. So actually, I got how, because you were trying to find the span, so you did a linear combination
Hmm.
with scalar A and B,
Hmm.
taking the two y1, y2 elements,
Hmm.
uh, and then you solved for A and B, and you
Yes.
found what are the A and B values which we can use. But after that, what is the logic you used? I didn't understand that part after that.
Okay. See, I am taking an element xy in R2. I can write it as a linear combination of 1, 1 and 1 minus 1.
Yes.
Okay. And this 1, 1 and 1 minus 1 belongs to y1 union y2. Okay.
Yeah. Mm.
What we are saying is 1, 1, 1 minus 1 belongs to y1 union
Y1,
y2. Okay.
yes.
So,
Yeah.
if I am taking any linear combination a1 1 plus b1 minus 1, it should belongs to span of y1 union y2, right? What is span of y1 union y2? It should be in the
It's a linear
form
combination.
ax1 plus a1 x1 plus a2 x2 plus etc. some akxk, where
Yes.
x1 etc. xk are elements of y1 union y2, a1 etc. ak are scalars. Okay, here I am just considering a1 x1 a2 x2, these two only. All others are supposed it is 0. A3 a4 everything is 0. So here it is
Correct.
a into 1 1 plus b into 1 minus 1, it belongs to span of y1 union y2. Okay.
Yeah.
So I have written xy as like this. I am taking any element from R2. Okay. I can write it as this. Okay.
Oh, okay.
So
I got it.
what does this
So
mean?
you,
R2 subset of
what you're
span.
saying is, so what you're saying is that since any element in R2 x, which is xy, can be written like this. This means that R2 is the same as span of y1 union y2.
From
Right?
this we can say R2 is contained in span of y1 union y2. But
Okay.
span of y1 union y2 cannot be more than R2, because span of y1 union y2, see,
it is in the plane only.
yeah, it
So
is in the
it
plane
can,
only. It is y1 union y2 is a
yeah,
subset of R2, a vector
it
space.
can be maximum.
Yeah, the
Like
maximum it is span is possible
can
is
be
R2 only. Correct?
R2. Yeah.
So
Yes.
both subset is satisfied. One is a subset of other and a superset of other. So it should be equal, right? So that is the logic
Okay.
difference.
Okay. Thank you. Yeah. Thanks.
Any other doubt? Anyone else? Yeah, if you have any doubt, you can ask now.
Will you be sharing this recording?
Yeah, I will share. So I will upload in the YouTube and the link will be shared. Like in the portal, you can see the live session recordings.
Okay.
Okay, if there is no other doubt, we can stop the session for today. Or if you have doubt, you can ask now. Okay, then let me stop for today. We will meet next Tuesday, the same time, for the week 3 session. So thank you everyone. See you next week. Bye.
YouTube channel name, ma'am?
Oh, sorry.
YouTube channel name.
YouTube channel, you can search NPTEL problem solving session. So in the portal, like there is a some separate tab for live session. In that, actually one more live session is there on Sundays, I think. So that YouTube link, everything will be available there. Like one Excel sheet we are sharing, so that will be available in the portal. So there, from there you will get. Okay.
Because I missed 2 sessions, ma'am, last 2 sessions, Sunday and Tuesday sessions. That's why I asked.
Yeah, it is available in the YouTube. You just log into the NPTEL portal as like whenever you want to see the video, week 1, week 2 video, you will log in, right? In the same way,
Yes.
after that week 1, week 2, week 3, there is one more tab, problem solving session, something like that. From there, there is a link. You will obtain an Excel sheet. In that, both the recordings, like Sunday recording, Tuesday recording, both will be available. Okay. Yeah. Okay, then let me stop the meeting now. Bye.
Yes, ma'am. Bye.
Okay, bye. പുറത്തുനിന്ന് പാർസൽ മേടിച്ചു. അയ്യോ, റെക്കോർഡിംഗ് ഓഫ് ആക്കി.